Okay, now for the introduction, this project explores the population growth of Brunei Darussalam from 2003 to 2023 using exponential growth modeling. By utilizing actual population data and mathematical modeling, the aim is to find a suitable exponential function that accurately represents the trend of Brunei's population growth over 2 decades. The goal is to better understand how the population has evolved and project future growth.
Next on the slide, we have the table of the data obtained for the population growth for Brunei. We have 2 columns. First, the data from the year 2003 until 2023, and the second column is the actual data we obtained from our sources. Now, let's look at the graph. As y against x. X actually represents the time for the year 2003 until 2023, and for the y represent the population data for the population growth of Brunei. Now, look at the 2 double color line. First, we have the red one. The red one is actually the data we obtained from using the particular solution that we use. Now, the blue line is actually represent the actual data from the predicted value come from the red line. Now, if you look closely, there's a slight gap around 2010 and 2015 and continued until 2023. This shows that our model cannot be used for the long-term cost. This can be only used with short-term cost because we can only predict it for the half of the year, as in 2003 until 2010. This can be caused by various factors, maybe because of economic value or maybe outbreak diseases that can cause the population growth to decrease than the actual predicted value from the solution that we use.
So for the discussion, the population model begins with a general form of an exponential equation, which is Pt equals to A exponential to the power of k and t. K is the constants that we need to search for, and t is the increasing value of our data. So using the initial condition from 2003, the t is 0, where the population was 346,637. We set the p0 to equals to 346,637, and we can find the a. So we got the a equals to 346,637 because the exponential will be to the power of 0 because the t is 0, so we would get 1. Okay, so now that we have our a, we can replace that a into our function. So the function become pt equals to 346,637 exponential kt. To find the constant k, we use data from 2004, so the t equals to 1. So we can ignore the t because the power of 1 means the same. So the equation become 352,911 based on our data equals to 346,637 to the power of k. And then we use the ln to eliminate the e, and then we get k approximately 0.018. Thus, the particular solution becomes pt equals to 346,637 exponent to the power of 0.018 t. So then, the equation is used to estimate the population from 2003 to 2023. The calculated values closely follow the actual recorded data, showing a steady increase in population over the years. A table and graph were created to visualize and compare actual versus calculated population values.
Now back on to the conclusion. The exponential model provides a close approximation of Brunei Darussalam population growth from 2003 to 2023. The results show a consistent graph pattern, which reflects the reliability of exponential functions in modeling real-world population trends. This model can be useful for policymakers, planners, and researchers when predicting future population changes and planning for resource allocation.
Hello everyone, today I'm going to talk about the trapezoid rule that we are going to be using for this question. and I will be talking about the function which are the integral of x equal to negative 1.3 to x equal to 0 to the third of 8x cubed times with the cos x plus 3. In this table, I will be explaining about the x column. As you can see, the x column, which is the x delta, will be subbed into the function cell. The function cell has equipped with its own formula to find the function value. Then the function value will multiply with the coefficient to find the height of each strips. And each of the strips will be totaled up and calculate to find the exact value for the width, which is multiplied by h over 2. The information that we extracted from the table and then plotted into the graph, we will get the exact shape of the curve of the graph. This shows that the graph is very curvy.
Hello everyone. Now I'll be talking about the 12th ordinates table for the 11th interval. In this table we have calculated 11 point of x starting from negative 1.3 up to 0. And just like Daing have explained in the previous calculations, all these points of x will be substituted in the function, and after we get the function value, we will be multiplying them with its respective coefficients to get the value of the height of each vertical strip. Now remember, only the first and last vertical strips only appear once, and the other will be appearing twice. So we'll be having 1 and 2 coefficients for each of them. Now after we sum it all up, we'll be having the value of 23.69, and that value will be multiplied with the width over 2, just like in the formula. And with that, we will be having the value of 1.4 for the 11 subinterval calculations. As you can see, when we plotted the graph with all the points of x that we have calculated before, we will be having this table of graph. The difference between the subintervals of 7 and 11s is that the calculations, which is the area under the graph, for the 11 subinterval will be more accurate compared to the 7 intervals. Okay, right now I will be giving you a thoroughly explanation about the task 2 calculations. In this task, we will be estimating the value of complicated mathematical expressions using the method called trapezoidal rule. This method helps us approximate the area under the graph, that if we try to find it directly, it will be too hard. So the function that we have here is fx equals to the square of 8 times x cubed cos x plus 3 in the bracket. So when we calculated the area under the graph from the point of x equals to 1.3 up to x equals to 0, using 2 different number of intervals. The first one is the 7 intervals, and the second one is the 11 intervals. Okay, bear in mind that each interval is like a small piece or small slice of the graph, meaning that if we have more slices, the more accurate our value will become. So for both cases, we found the value of the function at certain points and then add all up using the trapezoidal formula. So when we use the trapezoidal formula, our answers were 1.420 for the 7 intervals, while for the 11 intervals we found 1.400. This shows that the more intervals we have and the more slices that we use will give us more accurate results. This trapezoidal formula is a useful tool when we're trying to find the values that we cannot solve easily or when we cannot solve an integral of a complicated expression. That is all from us. Thank you.